These are the frequently asked questions for pre-calculus for section 3-4, day 2, without word problems. So 37, we have proved the quotient rule for logarithms, and so I pulled up the quotient rule here to remind everybody what that says. It says the logarithm base b of r over s, which gives us the quotient, is logarithm base b of r minus logarithm base b of s. So here's what we need to do. We need to get this in an exponential form that's going to make sense to us. So what we would do is we would say, all right, here's what I know. I'm going to make x equal the logarithm base b of r, because I can snail shell that, exponentiate it, and it'll look good. And let's make y equal to the logarithm base b of s, and I can do the same thing there. So if I snail shell, this says b to the x equals r. And if I snail shell this one, it says b to the y equals s. So now I start with the most basic piece that I can, which is this is supposed to be about division. That's what this is. So if I do some substitution, that is going to be b to the x over b to the y. And then I realize, well, I already know how to do that. We work with powers all the time. So r over s equals b to the x minus y. Now that seems like a really small thing, you know, to go ahead and go through that process. I'm going to give myself a little bit of room here, because at this point we should realize, you know what, the only thing we're missing here is logarithms. That's what we're missing. We need the logarithm language in here. So I'm going to take the logarithm base b of both sides, and the reason I do that is I want to produce those inverses over here so that says x minus y. So on the left-hand side, you'll notice I now have what I wanted, which is the logarithm base b of r over s, but on the other side I have this x minus y, and then the light bulb goes off, and I realize, wait a minute, I have what I want there also, because I said x equals logarithm base b of r, and y equals logarithm base b of s. So if I put those into their positions, watch what happens. Oh, that looks like a 5. That should be an S there. This will become logarithm base b of r minus logarithm base b of s. So that's what we do. We do some substitution so that we can exponentiate this, and we can see, hey, that is perfectly what we know about powers, and since logarithms are inverses, they should work that way also. So quick little proof there of what we have by using some substitution. Then you'd asked about a couple of graphing, and we've got 49 here. Says graph the function, analyze it for domain, range, continuity, increasing or decreasing behavior, asymptotes, and end behavior. And at first I thought, well, why are you asking about this one? We've gone over this, but this is different because we're talking about powers here. Now, when we look at this and we say, okay, we've got the logarithm of x squared, we should be thinking, well, powers become multiplication. So we're really just doing that. We are, but there's a little more taking place here. So I want you to remember that this originally came to us as x squared. But we'll go ahead and do this as we have in class, which is, we'll think about this as logarithm base 10 of x equals y, and say 10 to the y equals x, and we'll just go ahead and put some values in and figure out how this is going to work. So 10 to the negative 1 is 1/10, 10 to the 0 is 1, and 10 to the first is 10. But now, just like we did in class, we see that there's a 2 in front. And that 2, if we follow the order of operations, we'd have to do the logarithm of x first, evaluate that, and then multiply by 2. So what we really need is to take 2 times our y's. So 2 times negative 1 is negative 2, 2 times 0 is 0, and 2 times 1 is 2. So we won't be using those y's. So far what we have for our graph is we have a 1/10 and a negative 2, and we have a 1 and a 0, and we have a 10 and a 2, which would look like so. But that x squared Still bugs me. So I start thinking, what would that do differently? I mean, why that x squared? What would that be responsible for? And I realize that means I can put positives and negatives into this problem. So that means all of these x's are positive and negative. That's what that x squared is for. So that means I'm going to have some really nice symmetry on the other side. And that gives me a really unique graph. So now we have to go back and talk about domain and range and all of that. So this is one of these things is not like the others problems where there is a difference because we are talking about x squared in this problem. So our domain, we can't use 0. We can use positives, we can use negatives, but we cannot take the logarithm, evaluate the logarithm of 0. So our domain will be from negative infinity to 0, not inclusive of 0, and then hop over and go from 0 to infinity. Our range, that has not changed. Our range is negative infinity to infinity. And then it says we need to talk about continuity. Oh, this one is discontinuous. It is discontinuous at R0. And then it says increasing or decreasing behavior. Well, this time we actually have both. This is decreasing on the left-hand side of the y-axis. So decreasing from negative infinity to 0. And increasing from 0 to infinity. And of course, with increasing or decreasing behavior, we are not going to use any square brackets at all to include those. Asymptotes. That's our 0. So x equals 0. And then this one just happens to have both end behaviors this time. So limit of f of x as x approaches negative infinity is going to be infinity. It's going up. And then limit as x approaches infinity of f of x is also infinity because that's going up. So the interesting part of this one was the fact that we can put in both positive and negative values because it is x squared. What we can't do is put in the 0. Then for 50, you start thinking that same way, but you realize, wait a minute, if you're going to cube this one, then you've got problems because you can't do the negatives. So we still can't do the negatives. So this one is more similar to the problems that we were doing in class because we're going to rewrite that as 3 times the natural log of x, realizing we can't do a plus or minus with this one because we can't evaluate natural logarithm for a negative. So, in the real number system anyway, we're going to put some numbers in here and see what happens, but we're going to start with just ln of x, which is logarithm base e of x equals y. So this is e to the y equals x. This is why I've been harping about memorizing those e's to a power. And really, for a negative one, what we would need to know is that it's going to be a fraction, but it's 0.368. To the 0 power will give us a 1. 1 is, of course, 2.718. And then 2 is 7.389. But we do have a 3 in front of this. And we know that what we're going to have to do is evaluate the natural logarithm first and then multiply the output by 3. So all of these outputs need to be multiplied by 3. And again, we're not going to be graphing that middle. And this time there will be no right and left to our graph because this would be a power of 3, which means we cannot use the negatives. So 0.368 negative 3. And then we have 1 and 0. And we have 2.718 and 3. And 7.389 and 6. And this will be our graph. So we've got the natural log of x cubed, and we've got it all graphed, and now we have to go back and talk about all of that behavior. But this one is just like the other graphs that we did in class, because we have a base that's positive here, a base that's greater than 1. So for number 50, our domain is from 0 to infinity, and our range is all reals, negative infinity to infinity. It is continuous now, no breaks, continuous, it's always increasing. We do have our asymptote at x equals 0. We did not have any horizontal shifting. And this time again, we can only do one of the limit behaviors. And this one would be as we're going to the right forever. So as we're going to infinity, our graph is going up, which is infinity. So 2 very interesting little problems there.